So today, we're going to talk about one of the most, and I mean this, one of the most intuitive sorting algorithms out there, insertion sort. Now, that might sound all technical, but I bet you've actually used its core logic a bunch of times without even realizing it. And it probably happened while you were holding a hand of playing cards. Let's dig in. Seriously, think about it for a second. You get dealt this messy, random hand of cards. What's the very first thing you do? You kind of pick them up one by one, and you slide each card into its rightful place until, boom, your hand is perfectly ordered. Well, that simple, natural action, that's the key to understanding this entire algorithm. And hey, don't just take my word for it. This isn't just a loose comparison I'm making up. Computer scientists have been pointing this out for decades. The way our brains just intuitively create order from chaos with a deck of cards is almost a perfect blueprint for how insertion sort works inside a computer. Okay, so let's really break that down. The whole idea is that the algorithm builds up a sorted list just one item at a time. Imagine you draw a line in your data. Everything to the left of the line is sorted, and everything to the right is still a mess. To start, the sorted part is just that very first element, all by itself. So here's the official definition for you. You take an item, our next card if you will, from the unsorted pile. Then you scan backwards through your already sorted hand to find exactly where it belongs. You shift the other cards over to make a little room, and you just pop it in. And then you just do that again, and again, and again, until the unsorted pile is empty. All right, theory is great, but the absolute best way to really get this is to just see it in action. So we're going to walk through a simple, jumbled array and sort it together, one step at a time. And here is our array. The values are 9, 5, 1, 4, and 3. The goal, of course, is to get this into a nice, neat, ascending order. So following the rules, we start by saying that first element, the 9, is our initial, tiny, already sorted section. Easy enough. Okay, first real move, we pick the next element from the unsorted side, which is the 5. We call this our key. Now we compare it to what's in our sorted section, which right now is just the 9. Is 5 smaller than 9? Yep, so we shift the 9 one spot to the right, and we insert the 5 in that new empty space. And just like that, our sorted portion is now 5, 9. It's growing! You getting the hang of it? Let's do the next one. Our new key is 1. We look at our sorted list, 5, 9. We compare backwards. Is 1 smaller than 9? Yes, so we shift the 9 over. Is 1 smaller than 5? Yes, again. So we shift the 5 over. We've hit the very beginning of the list, so that's where we insert the 1. Our sorted section is now 1, 5, 9. And from here on out, it's pretty much rinse and repeat. Next up is 4. We compare it to 9, shift. Compare to 5, shift. But wait, it's larger than 1, so we stop and slot it right in between the 1 and the 5. And finally, we grab that last number, 3. We compare it backwards past the 9, the 5, and the 4, and insert it right between the 1 and the 4. And that's it. No more unsorted elements. The array is sorted. So it really all boils down to this simple 4-step dance that you just keep repeating. You extract a key, you compare it backwards, you shift everything bigger out of the way, and then you insert the key. You do that for every single element, and you're guaranteed to end up with a perfectly sorted list. Okay, so we know it's intuitive, it makes sense. But is it fast? That's the million-dollar question for any algorithm, right? And the answer, as it so often is in computer science, is, well, it depends. Let's take a look at the performance numbers. Now, this table tells a really interesting story. It shows this huge gap between the best and worst cases. The best case is something we call O of n, or linear time. That just means the workload grows in a nice, predictable straight line with the size of the list. But the average and worst cases are O(n squared, or quadratic time. That's where the work can grow exponentially, getting really, really slow as the list gets bigger. And this slide right here shows you exactly why that happens. In the best case scenario, the array is already sorted. The algorithm just zips through, making one comparison for each element and realizing, hey, nothing to do here. Super fast. But in the worst case, a list that's perfectly reverse sorted, every single new element has to be dragged all the way to the front. It has to compare and shift past every single other element in the sorted section. That is a ton of work. But here is a huge, huge win for insertion sort. Look at its space complexity, O of 1. This is awesome. It means the algorithm works in place.
It sorts the data right there where it lives, without needing to create big copies or new arrays. It only needs a tiny, constant little sliver of extra memory, no matter how ridiculously huge the list gets.
So given that its average performance is O of n squared, you might be thinking, well, this algorithm doesn't sound very useful in the real world. But that's not the whole story. It actually has a very specific set of strengths that make it the perfect tool for certain jobs. So where does it really shine? Well, for one, it's super simple to code, it's incredibly fast for small lists, it's adaptive, which is a fancy way of saying its performance gets way better if the list is already mostly sorted. It's also stable, so it won't mess up the original order of items that are equal. And it's online, which means it can sort data as it's coming in, without needing the whole list up front. Pretty cool, huh? Let's put it head-to-head with a similar algorithm, selection sort, to see a really interesting trade-off. The key difference is rates to memory. Insertion sort is constantly shifting elements around. That's a lot of writing. Selection sort, on the other hand, does way fewer writes. So if writing to memory is physically slow or expensive, like on some types of flash storage, selection sort might actually be the smarter choice, even if insertion sort is faster on paper. So what's the final verdict here? Insertion sort's beautiful simplicity is both its greatest strength and its main limitation, but that absolutely does not mean it's not important. In fact, it's quite the opposite. So let's wrap this up. Insertion sort is really the algorithm we have in our hands. It's how we think about sorting cards. It's adaptive, making it a fantastic choice for data that's already close to being in order. And most importantly, on a small scale, it's a true champion, often outperforming even the most complex, souped-up algorithms out there. And that brings us to one last really fascinating thought. For huge datasets, we use these powerful algorithms like quicksort or merge sort. But here's the secret. Those algorithms work by breaking big problems down into smaller and smaller and smaller ones. And when those little sub-problems get small enough, we're talking maybe 10 or 15 items, what do you think they switch to for the final sort? That's right. They call on our humble friend, Insertion Sort. It's the perfect reminder that in the world of computer science, sometimes the simplest tools are the most powerful ones.